So let's do another example that's a little bit more complicated and a little bit more interesting. Let's take this butane molecule, and let's go ahead and take our little eyeball and draw a Newman projection from this perspective, where we have the eyeball looking from carbon 2 to carbon 3. So pause the video, see if you can draw out a Newman projection for this. Okay, so if I was positioning myself from this perspective, and I was looking down carbon 2 to carbon 3, it would seem to me that more than likely this methyl group is pointing in a downward position. So that would be this. So just as a quick aside, this Me is just a quick abbreviation for methyl, which is just the same as saying a CH3 group. So I kind of use Me and methyl and CH3 kind of interchangeably. Sometimes I feel like Me is faster. So now if we drew out this molecule, you could describe the orientation between these two methyl groups, and we could say that these are in an anti-orientation. Let's pretend that we're going to rotate the front, and we're going to rotate the front by 120 degrees. Now keep in mind that the angle between this methyl and this hydrogen is 60. So this would be 60, and this would be 120. So let's redraw the molecule with the methyl being located up here. Now if we did this, the methyl's orientation between this methyl and this methyl is different than it was originally. We had this anti-configuration on the left, and now we're going to have this new configuration on the right, which is the gauche position. And so now let's do one extra rotation. And just like we rotated the front from the previous example, let's rotate the front again, keeping the back steady. So we're going to rotate this methyl and this hydrogen, and we're going to rotate the entire front face by 60 degrees. And after this last 60-degree rotation, we can say the orientation between these two methyls is in an eclipsed orientation. And so now if we go back to this wrecking ball analogy, we can try to comment on the overall energy of each of these Newman projections. And if you think of the wrecking ball, these two are very close together, so they're going to be clashing up against each other to a very high degree. In this gauche orientation, these two methyl wrecking balls are a little bit farther away, so the chances of them hitting each other are a little bit lower. And then here in this anti, the chances of them hitting each other are the lowest they possibly could be. And so in terms of energy, this eclipse orientation is going to be the highest energy, most unstable position, followed by the gauche, followed by the anti. And if we were to draw an energy diagram where energy is on the y-axis and rotations on the x-axis, we could try to draw out how that energy would look. So if we have the starting position over here at 0 degrees, and that would be this molecule right here, we could say this is the lowest position in terms of its energy, and this final position is going to be the highest energy. So this was a 60, 120, and 180 degree rotation. This is going to be the highest energy, so it's going to be way up here. And we're kind of neglecting the 60-degree orientation, but the 120, after we do that 120, it's going to look like this. It's going to be a little bit higher in energy than the beginning and a little bit lower in energy than the end. If we took the time to draw out the 60-degree Newman projection, we would see that we would get another kind of eclipsed orientation, and so that energy is going to be a local maximum. So the overall energy diagram would look something like this, where you get a local energy maximum, and then it comes down for a local minimum, and then it goes back up again for another local maximum. And it turns out that this final orientation is actually going to be a higher energy than this 60-degree orientation. So if you don't quite see that, try to draw out that 60-degree orientation and compare and contrast how this eclipse Newman projection is different than the other Newman projection that's eclipsed.